So I hope everything went okay on Monday. I didn't hear any howls of protests, so I assume. Okay, good. So, the idea there was to get a little bit of a handle on what the idea behind mirror symmetry is. And obviously there are lots of things one could say about that, but a lot of those aren't really in the realm of mathematics. They would require a very different background in conformal field theory, which again would be very interesting, but definitely this is not the class for that. So what framework is on mirror symmetry is interesting for mathematicians. It's sort of part of mathematics and symplectic geometry, hopefully, given that that's the topic of this course. Why did this idea become actually pretty important and widespread in math? And I would say the reason that people got so excited about mirror symmetry in the late 80s, early 90s, is that it actually does make really specific predictions in mathematics. But they're very strange predictions from the perspective of mathematicians, which is what makes them so interesting. All right. So as I mentioned before, when you're doing this sort of string theory with a Calabi-Yau M in the picture, so M throughout is going to be a real 6-dimensional, so complex 3-dimensional Calabi-Yau manifold. So one which has a Ricci flat Kähler metric. So we're looking at strings moving around in this manifold. And of course, that movement gives us a map of a 2-manifold into our guy. And one of the sort of things that's so appealing about string theory, sort of conceptually, is, well, sometimes particles kind of collide and interact with each other. And if you're thinking about strings, well, there's a natural way to think about such a collision. It's having a 2-manifold where 2 strings come in and collide and turn into 1 string, mapping. So of course, I'm skipping lots of physics here. I'm being very blasé about this stuff, but I'm just trying to give you a little bit of a flavor of where this comes from. That the cohomology of our manifold sort of manifests as certain operators in our quantum field theory. And so these are things that can kind of sit on distinct points in our space-time. No, not space-time, sorry. I'm going to mess up saying space-time and world sheet so many times. But there's this sheet that the string traces out, and different points on there can have operators sitting on them. And so there should be some product of these guys, of these operators, where we're trying to measure something like the correlation between the value of 2 operators on those 2 strings coming in, and then the value of a different operator on the string after they've collided. So I will probably just make this more and more confusing as I say more and more stuff, but this is the idea, that this sort of string theory means that we have a product that comes out of really topology, from my perspective, of these 2 strings joining up with each other and thinking about how operators on string 1 and string 2 before they collide, and different operator on string 3, how those all relate to each other. And I swear there will be some mathematics very soon. So, as often happens in quantum field theory, there's really some like Feynman integral sitting around this that you sort of think, oh, well, sort of all possible maps Riemann could have happened. I should think about how probable each one of them is. And so computing some expectation is some integral over the space of all such maps. And that's like, you know, pretty hard to do rigorously. But for certain special of these operators, so ones that are compatible with what's called the A-twist, let's not worry about what A-twist means, but this is just certain special guys that play sort of a special role in physics. Only pseudo-holomorphic maps of my Riemann surface into my Calabi-Yau end up contributing to this integral. And how all of the information concentrates on the pseudo-holomorphic maps. And I should mention here, I'm saying pseudo-holomorphic because this is the usual terminology, but that's the same thing as if I had just said holomorphic. So it just means compatible with the two complex structures, and putting some complex structure on my two manifold, making it a Riemann surface, and I look at almost complex structure on my Calabi-Yau, which maybe isn't the original Kähler one I started with. We'll see in a moment why you might want to do that, but which is compatible with my symplectic forms. This part of the stuff I'm talking about is going to be all symplectic. Yeah, okay, so this is exactly, sometimes I have these things where I say something and I'm like, oh yeah, I wrote that because that was something I wanted to say. So I'm starting with a complex structure in M, but I'm going to do something that actually only depends on its symplectic structure. And it's sort of useful, this is a kind of common theme, especially in symplectic topology, that you often want to do a construction that requires you to choose an almost complex structure. And then afterwards you say, oh, but my choice didn't depend which almost complex structure I chose. And that can actually be useful because then you have some freedom to be like, I don't like this almost complex structure. Let me choose a different one. All right, and since this path integral had a definition before I said anything about pseudo-holomorphic or anything about complex structures, I can do the computation in any complex structure. All right, so I have operators that correspond to elements of cohomology, but they have some different multiplication that has something to do with maps of my Riemann surface, possibly pseudo-holomorphic ones, into my complex manifold. And the object that comes out is what's called small quantum cohomology. And as I say, this has to do with computing correlations between operators at different points. So let me sort of try to give you a kind of pseudo-mathematical definition of this. So we look at the pseudo-holomorphic maps of CP1 into our manifold M. And I'm going to sort of ignore all analytic issues about like, wait, is that really a finite dimensional manifold? Like, what kind of space is that? I'm just going to sort of sweep that stuff under the rug, as is my want. There are people who have whole careers worrying about this stuff. All right, so of course, for any element of P1, I have an evaluation map, which says, okay, I take my map of CP1 into my manifold, I evaluate it at the point, let's say 0 or 1 or infinity. Those are going to be my usual choices, but you know, up to symmetries, all points in P1 are the same. And that gives me a map to my original manifold. And if I have two closed forms on M, so these are representing cohomology classes, the way I do this quantum product of them is I pull them back to these maps of P1 by evaluating at two different values. So I'm saying 0 and 1 here, but I could take any 2 points in P1 and I would get the same story. I pull back by those two different maps. I wedge upstairs on this space of maps, and then I integrate over the fibers of P infinity. Okay, and you can like rightly question, what do you mean integrate over the fibers? What do you mean like wedging on this thing you haven't proved is a manifold? But let's sweep all that under the rug. And then there's also an extra term here, which is I have some formal parameter Q, and I'm raising that to the integral of the pullback of the symplectic form over the P1. So every point in M3 is a map of CP1 into my manifold. So for every such point, I can pull back the symplectic form and integrate over P1. And this is usually what's called a degree. So I should just say this is the degree. And if you're used to degrees in algebraic geometry, right, this is the same thing as the degree of a curve in P2 with respect to the Fubini-Studi form. You pull it back by the map, integrate it over the curve, you get a number, which is actually the degree in the sense of algebraic geometry. All right, any questions? Okay, so this is a weird thing, I admit. So how do we think about this? Well, if I send Q to 0, then all maps of positive degree end up getting lost. And so as I send Q to 0, I only get the contribution from constant maps. Right? Just take CP1 and I map it all to one point in M. And if I do that, then actually my product just becomes the usual wedge product of forms. Somehow this pulling back and pushing forward doesn't do anything. So this is a deformation of the usual wedge product on Deform cohomology classes. And I'm going to use A of M to denote the cohomology with this star product. And I'll note this is actually bigraded by, this is isomorphic to the sum of the Dolbeau cohomology, which can be given this deformed quantum product.
Sorry, I had a question. When you said integrate over the fiber P infinity, where does this P infinity come from?
Well, there's a point in CP1 whose name is infinity. And there's a map from the space of maps of P1 into M to M, which is evaluate the map at infinity.
Oh.
And I mean, there's nothing special about 0, 1, and infinity. I could use any 3 points in P1, and there's a Möbius transformation that sends those to 1, 0, 0, 1, and infinity.
Oh, okay. Okay, thanks. I thought you meant like CP infinity or something. I was like, what? Okay.
No, no, no.
All right, thanks.
All right. So I'll just note, there's another way to think about this, which I think you'll sort of more often see, which is, remember that we have Poincare duality. So I have a perfect pairing between the jth degree in cohomology and actually my M is always 3-dimensional. So the 3 minus jth degree, which is wedge and integrate over M. And so I can rewrite this as a function of take the quantum product of A and B, take this inner product using the Poincare pairing with gamma. And now what you're getting is pull back alpha by the map of evaluation 0, pull back beta by the map of evaluation at 1, pull back gamma by the map of evaluation infinity. Or again, you could take any 3 points you want in CP1 and integrate that over M3, again with this funny Q coefficient thrown in to track degree. If you don't really like de Rham cohomology and you would rather think about like actual cycles, submanifolds in your manifold, think of those as homology classes, well then, excuse me, this Poincare pairing becomes intersect your two cycles and count the number of intersections. So we can think about doing the usual product of A and B, doing that with gamma as, well, if alpha is Poincare dual to a cycle A and B is Poincare dual to a cycle B and gamma is Poincare dual to a cycle C, then just doing the boring wedging and pairing with gamma is the number of intersection points in A, B, and C, as long as I deform A, B, and C to be generic. And of course, as long as they have the right dimension, that there's a finite number of isolated intersection points. What this quantum product picks up instead is the number of maps from P1 into your manifold that sends 0 into A, 1 into B, and infinity into C. And again, constant maps like that pick up actual intersection points, and that's what you get if you send Q to 0. And then for higher degrees, well, you could have some cycles that don't intersect, but have some interesting P1 that hits one of them here and one of them here and one of them here. So this is sort of, it's a strange story, but it gets you this interesting thing. And I should emphasize, since this is a symplectic geometry class, it only depends on the symplectic structure. It doesn't depend on anything about which complex structure you choose, except you have to be careful. I mean, somehow I've been sort of skipping saying anything technical about this space M3 existing. I've just been kind of assuming it's a well-defined existing thing. So in general, this is a really kind of long and complicated story to sort of sort out what the right way to make this all precise is. But for 3D Calabi-Yaos, it's not too bad. So if we choose a generic almost complex structure, and I do have to choose a generic one, I can choose like dumb, degenerate ones where this doesn't work out, then in each homology class, there are finitely many generically injective pseudo-holomorphic maps from P1 into my manifold up to reparametrization. So I could reparametrize P1 and get an infinite number of them, which represent any given homology class. So there's going to be infinitely many such maps, but if you fix what the degree is, there are only finitely many of them. And for a given degree delta, I should have said that delta is the name of this homology class. There are only finitely many such maps that represent this class, and we can do an assigned count of the number of such maps in delta. And again, this is going to be independent of the choice of almost complex structure, as long as it's generic enough. And in general, I have to be kind of careful about counting these with the right kind of sign, counting them with multiplicity. You know, you can have this kind of usual, you know, somehow you should think of this as an intersection problem, right? You have the space of all maps of P1, and you're applying this condition of being pseudo-holomorphic to them. And so sort of sometimes that condition becomes degenerate at given points. So in just the same way that, like, you know, all degree n polynomials have the same number of solutions as long as you count them with respect to multiplicity, you have to be worried about exactly those kind of issues. But there is a well-defined number that counts sort of what's notionally supposed to be the number of these curves. And so you can use this to define quantum multiplication. Since we're only talking about 3D Calabi-Yaos, this is only interesting when you have 3 degree 2 classes here. So I'm going to assume that for this formula, alpha, beta, and gamma are all in H2. I could even have said H11. All right, and this quantum product of them, well, there's a contribution from the constant maps, which is just the usual, take the wedge pairing and pair with gamma, count the actual intersection points. And then I have these contributions coming from these pseudo-holomorphic curves. And I have the number of curves that represent this homology class delta. And then I have these pairings between, so this is the pairing between second cohomology and second homology. Or if I think of Poincare duality, I can think of the dual of that as a 4-dimensional manifold. And I look at how many times it intersects the 2-dimensional submanifold given by this homology class. And where these terms come from, alpha, alpha paired with delta, beta paired with delta, gamma paired with delta, is that I'm mapping in CP1 with its image being this particular curve up to reparametrization. So the point is somehow I'm fixing basically what the image is, which hopefully is actually diffeomorphic to CP1, but it might have self-intersections or something. And I have to look at, I have to send 0 to something sitting on the cycle dual to alpha, and send 1 to something on the cycle dual to beta, and gamma, infinity, to something sitting on the cycle dual to gamma. And these numbers are the number of different possibilities. So the pairing of delta with alpha is the number of different places I can send 0. The pairing of beta with delta is the number of places I can send 1. And the pairing of gamma with delta is the number of places I can send infinity. And I can choose all 3 of those totally independently. Basically because I have fractional linear transformations that send any triple of distinct elements of P1 to any other triple of distinct elements. And then each one of those contributes this factor of Q delta over 1 minus Q delta. You can rewrite that as Q delta plus Q2 delta plus Q3 delta. And that's the contribution coming from the fact that there are ramified covers of P1 by P1. I think that's right. Yeah. All right, cool. Yeah, as I say. So again, this is just, I wrote in a paragraph what I just said out loud. This pairing of alpha with delta, the number of intersection points between the P1 and the 4 submanifold, which should be representing.
Can I ask a question?
Yeah, of course.
Just regarding the deformation parameter Q, right? Because I've seen, like, just algebraically, when people think about quantum groups, they sort of write down the commutators or the Lie brackets of these quantum groups, and they say like, oh, we don't want Q to be a root of unity. So I can sort of see that here as well, that you don't want Q to be a root of unity. But like when, is there a way to think about it geometrically?
I would want to think about that. I mean, here yeah, I don't think I want to say
Okay.
When I think about Q, like, right, I mean, there's sort of serious questions about like convergence and this sort of stuff, right? I'm not thinking of Q as a number. I'm thinking of as a formal parameter. And everything I'm going to do involves just leaving this as a power series in Q. And there's sometimes where you want to think, oh, well, does that power series converge to an actual function? So, you know, I'm not saying that's like completely out, but that's something different from what I'm doing here. I'm just thinking of Q as a formal thing. And yeah. So let me. Oh, and actually should have, you'll note here, here I paired against the symplectic form. So actually I should have the real number given by the pairing of this guy against the symplectic form. And again, you know, somehow like in different contexts, you'll want to think about fixing the symplectic form or want to think about varying the symplectic form, and then like thinking of Q as like a variable depending on the symplectic form you choose. So as I've written it here, I'm looking at Q raised to real numbers, and there's no reason that right, I'm not assuming that my symplectic form is integral. So have to be a little careful about that. So it's not even clear kind of the way I'm writing this that it's going to make sense to specialize this to an actual numerical value. And indeed, if I tried to, you know, this power series expansion is only valid when Q has norm less than 1. So indeed, like this power series expansion here I've used just wouldn't make sense if Q were on the unit circle. All right, any other questions? Okay. So this formula defines deformation of the cohomology of M as a ring over, I mean, here I put C Q to the R, so all real powers of Q. There are various ways I could fix that and make that a little nicer, right? Because even though I'm not assuming these exponents will be integral, they also couldn't, you know, be like totally weird, irrational things, right? Delta is an integral cohomology class. So I know that an integral homology class. So I know that pairing integral homology classes with my symplectic form isn't going to give me totally random stuff. It's going to give me the integers times some fixed scalar. All right, so that's Gromov-Witten theory. It's a big story, so let me not get too drawn down into it. When I was in graduate school, actually I think this was my first semester or something, or maybe my second one, there was a topics course on Gromov-Witten theory by Giventhal, who's sort of one of the big names in the subject, but the name he chose for it was Gromov-Witten theory, on her knees, question mark. And we learned afterwards that the idea was that somehow like he thought that Gromov-Witten theory had been on her knees, but maybe was now standing up and getting ready to walk. But boy, it really didn't come across in the name. All right. Because I think Gromov-Witten theory is off her knees. She's doing all right now. Okay, so this sounds like a story where I tell you, oh, there's this interesting product on cohomology where you deform. And in order to figure out what this product is, then you find out how many curves of a given degree there are, and that tells you your quantum cohomology product. But that's really hard. It's really, really, really hard to actually calculate these numbers. So mathematicians have been thinking about these kind of issues for over a century. This was kind of one of the earliest style of problems that people considered in algebraic geometry. Obviously, they were using the usual complex structure on algebraic varieties, but they were thinking about versions of these problems. And it was really hard to do calculations and come up with crazy big numbers. And who knows what the heck they mean. So in physics terms, what's going on here is we have a quantum correction to the multiplication of these operators. There's some classical theory underlying this picture where you would just get the usual cup product multiplication. And it's just always hard when you have quantum corrections to things. As I keep saying, quantization is an art, not a functor. So, but you'll remember the whole point of this is we're supposed to be talking about mirror symmetry. So as I said before, you make some choice somewhere in the guts of this theory differently, and you get the physics not of M, but of some different Calabi-Yau M check. And the quantum cohomology of that other Calabi-Yau shows up on M somewhere different. So it has to be hidden inside the physics on M, but it's hidden in there in a different way from the quantum cohomology. It's going to be a different kind of operator. And instead of being compatible with the A twist, it's compatible with the B twist, whatever the A and B. All right, just because it's awful to try to talk about mirror symmetry without saying something about this. Ultimately, what do I mean by this? I mean that attached to these Calabi-Yaus, we have n equals 2 superconformal field theories. And those have two things inside them called the A twist and the B twist. They're actually connected to these two twos. And these ultimately come from the fact that I have an SO2 in the picture, because I have a two-dimensional field theory. And SO2 is the circle, but the circle can act on itself by rotating clockwise or counterclockwise. And the two twos have to do with how many supercharges are, come from rotating clockwise and how many come from rotating counterclockwise. And so like what we have is an equivalence of these theories that swaps rotating clockwise and rotating counterclockwise. All right, those correspond to the A and B twists. So it's one of these things where it looks totally arbitrary, right? Which why is rotating counterclockwise better than rotating clockwise? But you swap them and you get the physics that comes from a different Calabi-Yau. So how the quantum cohomology of the mirror shows up inside the theory attached to the original manifold M is a different space. It's one that's defined purely in terms of the complex structure, whereas the quantum cohomology was defined purely in terms of the symplectic structure. So here I'm taking the holomorphic tangent bundle to M. I'm taking its pth wedge power, and I'm taking the sheaf cohomology of that. So I'm sorry, there are probably some of you for whom sheaf cohomology is not a very familiar thing. We'll see that this is actually pretty familiar in a moment. So this is just sort of the general definition. But since M is Calabi-Yau, it has a holomorphic volume form on it. And, oh, I wrote the wrong thing here. fix that. Contraction with that holomorphic volume form defines an isomorphism between the pth wedge power of the tangent bundle and the n minus pth wedge power of the cotangent bundle. Both of them holomorphic. So this is basically this, this holomorphic volume form. I can write it as like dz1 wedge up through, well, again, in this case, dz3. And so if I have a vector field or a wedge of vector fields, I can write them out in these coordinates, have it eat this guy, and I'll be left with a form of the complementary degree, so an n minus p form. And the sheaf cohomology of, I wrote the wrong thing. Yeah, oh no, I did write the right thing. Okay, great. And the sheaf cohomology of these guys, that's the Dolbeau cohomology. So actually, because M is Calabi-Yau, this wedge powers the tangent bundle, that's just the Dolbeau cohomology, but indexed in a weird way. So this guy is isomorphic to the Dolbeau cohomology, not quite canonically, because I have to choose this volume form, but the volume form is unique up to a complex scalar. And so what am I finding here? I'm finding the reflection of the Hodge diamond, right? I'm getting a bi-graded algebra where in degree 0, 0, 0, I'm getting H3, 0 of M, and then H2, 0, H1, 1. I'm sorry. Having a momentary brain freeze there. Okay, so this is, if I keep going here, this is exactly the Hodge diamond reflected through this axis. So looking at these wedge powers of the tangent bundle will give me a reflected version of the Hodge diamond. This is all actually getting rather large when we actually know that in 3 dimensions, the Hodge diamond isn't very big. I have C, 0, 0. So any 3D Calabi-Yau is going to have a Hodge diamond where the outer edges look like this. And the only interesting part is in the middle. And so the interesting part is exactly that here I have H21M. Here I have H11M.
Is this Serre duality, by the way?
Oh, let's see. No, I haven't used Serre duality yet.
Oh, okay. But this is not the mirror symmetry thing. It's like, this is only a reflection in a diagonal, but this isn't the whole story with the rotation, right? Isn't that what we want?
No, this is the symmetry of the Hodge diamond. Hodge diamond is always invariant under 180-degree rotation. So remember, there are like a bunch of reflection and rotation symmetries that the Hodge diamond already satisfies.
And this is one of them.
No, this is an extra one. This is not.
Because it seems like the only thing you've used is the fact that this manifold is Calabi-Yau.
Well, yes, but this is a different space.
A different...
Right? Sorry, I'm looking not at the cohomology, I'm looking at a different algebra, which happens to be isomorphic to the cohomology as a vector space. But that isomorphism like completely messes up the grading in the algebra structure, right? So what it does to the grading is it does this flip in one of the gradings and not in the other one.
Okay. All right.
So, and I should emphasize, right, this, I define this guy BM. So yeah, reflection of the Hodge diamond. Let me like write this out as a theorem. Theorem BM is a bigraded algebra such that the reflection, or the, let me just say the dimensions of graded pieces are the reflection of the Hodge diamond of M. And are not equal to the Hodge diamond itself.
Okay, got it.
Yeah. So we'll come to this example later, but you know, there's an example of the quintic in P4, whose Hodge diamond looks like 1, 1, 1, 1, 1, 101, 101. All right, and if I compute, so these are the graded dimensions of AM. If I compute the graded dimensions of BM, they're 1, 101, 101, 1, 1, 1, 0, 0.
And then does the question then become, is this BM the Hodge diamond of some other manifold? Like, is this the actual cohomology of some actual manifold?
Right. So is there a manifold out there whose Hodge diamond is this guy? Right. So, you know, there's a part of this story which is all just happening on M itself. But indeed, because M is Calabi-Yau, this reflected Hodge diamond looks exactly like the Hodge diamond of another Calabi-Yau. Like it looks like it could be the Hodge diamond of a Calabi-Yau. Is there one out there that satisfies that? And in this particular case, the answer is yes, absolutely yes. This is just to emphasize, this is a graded algebra whose total dimension is the same, but whose graded dimension is different. It's reflected. All right, and this is supposed to be some, so this comes from the B twist instead of the A twist. So before everything only depended on the symplectic form, now everything's only going to depend on the complex structure. And in the symplectic picture, this H11 played an important role because the only way you can deform a symplectic form is by changing its cohomology class. And so these are the directions that we can deform our symplectic form. Here I said something about H11 since we only want to stay Kähler, but like actually if you're Calabi-Yau, then just all of H2 is H11. So it's hard to even say what the difference would be. All right. So on the other hand, if I look at the degree 1, piece of this B algebra, so this guy, that tells me about how I can deform my complex structure. So by definition, I'm looking at the first sheaf cohomology of the holomorphic vector fields. And I apologize because I don't expect you to actually know what H1 is, but let me explain something about where this comes from, because this is a story worth knowing. So I'm trying to tell you what it looks like to infinitesimally deform the complex structure. So we can think about this as we take our complex manifold, we cut it up into neighborhoods, and we think about our original complex manifold as taking those neighborhoods and gluing them together. And what we do now is we deform that gluing map. We change the gluing map a little bit by an infinitesimal automorphism of the overlap. So sort of think about here's ui, here's uj. To put the manifold together, I glue these by identifying some points in ui with some points in uj. And if I have some holomorphic vector field on the overlap, I can use that to change how they glue together. An infinitesimal amount, right? So I don't have to worry about like actually integrating things. I just think of a vector field as sort of for the first epsilon amount of time, I flow along that vector field. And because epsilon is infinitely small, it's all okay. So this is actually going to define having a section over all the overlaps. The fact that I actually need to glue things together gives me a co-cycle condition, right? So if I have a third guy, UK, that overlaps with UI and UJ, well, I'm deforming the gluing map between UI and UK, and I'm deforming the gluing map between UJ and UK, and I have to make sure that I do all those deformations in a way that's compatible. And that's exactly a co-cycle condition for this guy to define me a class in H1 of this tangent bubble. So this is sort of quite often, whenever H1s are often a source of deformations. And you should usually think of this as like you have your manifold, you cut it up into a cover, and then H1 is something about what happens on the overlap. Right, so there's a co-cycle condition. Then, of course, it being a cohomology, there's some co-boundary condition, which is that you didn't take a global vector field and just deform everything with respect to that global vector field. Yeah. Well, actually, I didn't take a vector field on each one of the UJs and deform everything on UJ with respect to that. That's actually the right co-boundary condition. All right. So out of this, an infinitesimal deformation of my complex structure gives me a class in H1 of the holomorphic tangent bundle. This is called the Kodaira-Spencer class. Kodaira-Spencer theory is the sort of name for thinking about deformations of complex manifolds this way. And as we discussed before, that's the same as this bit of the Hodge diamond, H21. Or more generally, it would be Hn minus 1. So again, one of these sort of usual stories here is this bit of the Hodge diamond corresponds to deformations of symplectic structure. This bit of the Hodge diamond corresponds to deformations of complex structure, and reflecting Hodge diamond switches those. So I shouldn't have used red there, I should have used blue. And so whatever guy I'm going to come up with, the deformation of symplectic structure on my original M is going to have to correspond to deformation, complex structure on this dual guy, whatever it is. The ring structure here is the one induced by wedge product. All right, I think I'm going to pause for a moment. You guys can ponder what we've discussed and see if you have any questions. So yes, as I was saying, we defined this B-side ring. I'm exactly trying to say it's a ring by this sheaf cohomology of wedge powers at the tangent bundle. The wedge product induces a ring structure on this guy. Those of you who don't know about sheaf cohomology are just going to have to believe me that the degrees of the sheaf cohomology add the number of wedge powers adds by just how wedge product works. So the actual interesting part here is that in order to define correlation functions, you need a product and you need a trace function. So you can define the correlation of three operators by taking their product and then applying the trace to that. In the quantum cohomology side, the product was deformed and the trace was just kind of the usual thing from Poincare duality of integrate over the manifold. Now, the product here on the B side is just kind of the obvious thing, do wedge product, but I also need a trace. And where this trace is going to come from is if I look at the top wedge power of my holomorphic tangent bundle, and I look at the nth cohomology of that, so let's not worry about that just yet. By the Calabi-Yau property, that top wedge power of the tangent bundle is trivial. It's a trivial bundle. I'm using O here in the sense of algebraic geometry. This is the trivial line bundle. And that isomorphism is you take this top element of the top wedge power of the tangent sheaf and you contract it with the holomorphic volume form, right? So that's what I have written here, contract with the holomorphic volume form, which unfortunately everybody calls capital omega. So that's not a symplectic form, that's the holomorphic volume form. That takes me to Hn of the structure sheaf. Well, the top wedge power of the cotangent bundle is also trivial. So I can now multiply this by the holomorphic volume form and get something in the top wedge power of the cotangent bundle, taking Hn of that. And that is using this isomorphism to Dolbeau cohomology, the same thing as H2n of n. So that I can just integrate over C. And for Matthew, this is where I'm using Serre duality. So Serre duality exactly tells me that this Hn of this top wedge power of Hn of the canonical bundle is the same as functions, is constants, and the map is integrate over the manifold. So you could either sort of use this isomorphism to cohomology and then integrate, or you could say this is a consequence of Serre duality. And then if you go look at the proof of Serre duality, like Griffiths and Harris, they're like, oh, well, integrate over the manifold. So it's all the same proof. All right. So this defines a trace map from Bm to C. So there's sort of 2 points about dependence here. There's one not especially important point, which is, oh, wait a second, I chose a holomorphic volume form. I could multiply that by any complex number, get a holomorphic volume form, and of course I would get a different trace. So somehow this trace is only really well defined up to multiplication by a complex number. That's a manageable issue. You can choose the right normalization for that guy. The other is that I guess I know I said this somewhere. Yeah, all of this depends on the choice of complex structure. So as before, there's kind of, do I want to think about having a fixed symplectic structure, or do I want to think about what happens as the symplectic structure varies? Here I have to think about, do I want to think about one fixed complex structure, or do I want to think about what happens as the complex structure varies? And really, you want to think about the latter. Yeah, so this is just kind of writing out, when we were talking about quantum cohomology, I said sort of the interesting case is taking elements of H1, 3 elements of H11, and computing their 3-point function, because we have a threefold. And similarly here, the kind of interesting thing to do is take 3 operators that correspond to complex deformations and compute their 3-point function. Where I'm writing out almost the same formula here, but you can think about what happens when I take alpha, beta, and gamma. Well, I need to take omega and contract that with A wedge beta, wedge gamma, which is the same as just contract it with gamma, contract it with beta, contract it with alpha, and then multiply by the holomorphic volume form and integrate over it. All right, so the sort of thing to keep in mind here that's different, why is it worth looking at the A side and the B side? So unlike the A side, where you have to do this, you have this horrible like, oh my God, what are the pseudo holomorphic curves? This is just an integral, like just a normal old integral that, you know, maybe takes a little work to do properly, but you know, you can attack using the usual methods of multivariable calculus. So it's a classical calculation. So it's sort of just morally, it should be much easier than the quantum calculation on the A side. All right, so I'm trying to sort of state this as a theorem, but I kind of copped out here. If I have 2 Calabi-Yaus, M and M check, such that they have equivalent superconformal field theories with the A and B twist swapping, like I mentioned before, then in particular, you're going to get the quantum cohomology of M is isomorphic to this B chiral ring. Yeah, gave this a name so I wouldn't have to stumble over it. Now I'm stumbling over it anyways, but B of M check. So A of M is isomorphic to B of M check, and in fact, of course, it's also true that B of M is isomorphic to A of M check. And this is fairly tautological, right? I didn't really tell you what it means that these guys have equivalent superconformal field theories, but this is basically a formal consequence of that. These guys are isomorphic as bigraded rings with trace, and in this case, we call M and M check a mirror pair. All right. Any questions? So it's kind of a remarkable fact that this ever happens. And I should say, I'm not sort of, I don't think I put any precise statement about this down here, but we know a lot of examples where this happens. So there's extensive calculational evidence behind this, and a large, though by no means comprehensive, set of varieties where we genuinely know what to do. We know how to start with one of them and construct the mirror. So don't I'm not going to get deep into how you do those because that's a lot of complicated algebraic geometry. And we don't have, sort of one completely unifying construction, but we know a lot of examples where we can prove this. So I wanted to talk about sort of the most famous example, which is kind of the granddaddy of them all. So we take CP4 and we look at the zero set of a generic degree 5 polynomial. So one example is the sum of the fifth powers of the variables. One thing that's worth thinking about, how many choices do I have for what the polynomials are? So if you just count, excuse me, monomials, you get that there are 126 dimensions on which you can vary. But that's not a good count because you have PGL5 acting on your projective space. So you could have a variety and then you could move it over somewhere else with PGL5 and it would be isomorphic as an abstract complex manifold. And you can take your polynomial and multiply it by a scalar and you get literally the same zero set. So this is not really the right way to think about abstract deformations. You have to account for the action of GL5 on the set of polynomials, right? So I said, oh, PGL5 acts on the projective space, but you can multiply your polynomial by a scalar and get the same variety. So when you account for that together, you need to look at GL5 acting on your set of polynomials. And that gets rid of 25 dimensions. Right? GL5 is 5 squared, 25 dimensional. So the actual answer I get is that I should get 101 deformations, not to be confused with 101 Dalmatians. And you can verify that this is the set of all possible Kodaira-Spencer classes. So you're getting all possible deformation directions of your variety just by varying your quintic polynomial. All right, on the other hand, if I look at H11, that's one dimensional and it's spanned by the pullback of the Fubini-Studi class, right? So the zeros of this polynomial, that's a complex submanifold of CP4. So it inherits a Kähler structure from CP4. And it turns out that's all the simplex forms you can have. So there's only kind of one interesting computation to do, which is the 3-point function of the symplectic form with itself 3 times. So what does this look like? Well, I can compute the first coefficient, no problem. That's, I take the usual wedge power of the symplectic form of itself 3 times and I integrate that over the manifold. And a little bit of calculation shows you that that's 5. And I should say that the reason is sort of this triple wedge product. If I do that on CP4, that's dual to, Poincare dual to the class of a line in CP4. So integrating that over my subvariety is asking how many times does a line in CP4 intersect my subvariety? That's its degree. So I get 5. All right, but then I have these other terms, the interesting ones, that involve this number ND. So remember, the way I defined it, ND is the number of pseudo-holomorphic curves of a generic almost complex structure on this symplectic manifold. So it's actually an extremely difficult open problem, whether in the usual complex structure, there are finitely many curves of a different degree, of a given degree. So this is known for D less than or equal to 11. I'm at least fairly sure this is still open. I was doing a little bit of research right before class, and I did find a preprint on the archive from like the 90s that claimed to prove this, but it didn't have any reference, like no one had ever referred to it. So I don't think it was ever published or generally accepted. It's an unfortunate thing. Anybody can put anything on the archive, and you can't be totally sure it's verified. Now, given that we don't actually know that the number is finite, you can be pretty sure we won't be computing these by counting curves by hand. Just should give you a feel for this is a very challenging thing to do. So we would have much more luck if we found the dual, and then we would just need to do some integrals over the dual. It might be a little bit of work, but somebody else probably already did that work anyways. All right, so the dual actually ends up being kind of interesting. You look at the diagonal matrices with fifth root of unity entries along the diagonal, whose determinant is 1. And then you mod out by the scalar matrices inside there. So the identity matrix times the individual fifth roots of unity. So the result here is isomorphic to Z mod 5 to the 3. This is a subgroup of PGL5C, so it acts on CP4 by acting on the coordinates by these scalars. So the reason I mod out by the multiples of the identity is those act trivially on CP4. All right, so this is going to preserve M if my polynomial has the following form. I only use the fifth powers of variables or the product of all the variables. And that's why the determinant being 1 is so important. If I hadn't assumed determinant 1, I would act, I act on this product of variables by the determinant of the matrix. Or maybe it's inverse. So I need that to be 1 for this guy to be invariant. And it turns out the construction of the dual in this particular case is it's actually the resolution of singularities of the quotient. So I take my hypersurface, I mod out by the action of this finite group. That's a singular algebraic variety. And I choose a resolution. And I should emphasize that is choice. There isn't one unique resolution. And this has to do with the fact that M doesn't have a unique complex structure, right? I have a lot of different options for what its complex structure looks like. That translates on the dual side to there being a lot of different choices of possible resolutions for M check. All right. Oops. So I'll note, here I actually wrote basically the most general polynomial possible in this form. If I had any non-zero coefficients in front of these fifth powers, I could get rid of them by acting by diagonal matrices in GL5. So up to the action of GL5, I can move these fifth powers to all have coefficient 1. And so I only have one interesting parameter left, this coefficient C. And then if you think again by the fact that you can act by fifth root of unity entries that don't necessarily have determinant 1, I can multiply this C by a fifth root of unity without changing the variety. So the sort of natural coefficient to use for actually deforming the complex structure in here is C to the fifth. And for various reasons, people prefer the reciprocal of that, 1 over C to the fifth. So this is a variable, this X. This is choosing different complex structures on the same underlying manifold, just as before we might have varied the symplectic form. And if you look at what I told you the Hodge diamond of the mirror was supposed to look like, and I passed it. So the Hodge diamond of the mirror, there's supposed to be only one complex deformation direction. So this X, this is measuring how I can deform the complex structure on this mirror, whereas I have a huge number of different possibilities for the Kähler directions. Right. So dependence on C on the B side should match up with dependence on the Kähler parameter on the A side. Okay. So I have to admit, as I was preparing this, at some point this example kind of defeated me. There are some complicated things going on. So let me try to kind of zoom out a little bit and tell you kind of morally what's going on, and then we can look at the formulas together. So how am I supposed to think about these B-side correlation functions? Well, you know, I sort of stated everything saying, well, you should think about a fixed complex structure on this guy and do blah, 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 blah. But actually, it's much better to think about these guys as functions of X and how they depend on X. And maybe I should say some words here. Since these guys are effectively topological, if I deform complex structure, the ring BM, so I'm tempted to say it doesn't change, but it's a little bit stronger than that. I mean that if I give you a path in the space of complex structures from M to M prime, then I get an induced isomorphism from BM to BM prime. So that is, I get a connection. On the vector bundle. BM times the space of complex structures. So I have some underlying space of complex structures on my manifold. Over each one of those guys, I have a vector bundle whose fiber over a given complex structure is the ring BM attached to that complex structure. And that vector bundle has a flat connection. And you can actually write these correlation functions in terms of that connection structure. In particular, right, we talked about the fundamental thing you want to compute correlations of is deformation directions thought of as elements of degree 1, 1 in my B algebra. So I get one of those at each different complex structure by looking at a vector field like x ddx. So on each one of these guys, x ddx tells me a direction that I can deform my complex structure, and thus gives me an element of this B algebra. And so it makes sense to compute the correlation of this guy with itself 3 times, and then think about how that varies with respect to x. And basically, because of this connection story, that has to satisfy some differential equations. And we can kind of pin down everything that's going on by looking at the differential equations these guys have to satisfy. I'm running out of time and I'm not such a big expert on this anyways, but you get these kind of differential equations like, oh, this triple correlation satisfies x ddx is this rational function. All right, and then at some point I decided, well, if I try to actually like recopy these formulas, I'm just going to make a bunch of disastrous mistakes and I'm not going to be able to explain what's going on anyways. But out of looking at like power series solutions to the differential equations that appear, basically what happens here is you have some differential equation, you look at its unique holomorphic solution. This is actually the integral of this guy over some fixed cycle, which they call gamma zero. Similarly, this is the integral of this guy over some other fixed cycle. So one of the sort of terms you'll hear tossed around a lot in this picture is periods, which means as I vary the complex structure, I have this unique holomorphic symplectic form up to some normalization. What is its integral over different subvarieties or different cycles inside my complex manifold? And how do they vary as I vary the complex structure and thus vary the top form? So I get these differential equation these guys has to satisfy, and some slightly complicated looking power series solutions to those. And the key thing here is this x, that's my x. That's the variable I was using before to parameterize the complex structures. And the really hard part of getting everything to work out is exactly how do deforming the complex structures and deforming the symplectic structures match up. That's what's called a mirror map. And the formula for that, well, it turns out to be slightly horrible. It looks like this. So Q, that's the Q I had in the quantum cohomology, corresponds to this huge power series in X. So my correlation on one side, the correlation between three copies of the symplectic form, it sort of carries what these numbers of holomorphic curves are, ends up being some slightly complicated expression. So this doesn't look that bad, but note, it involves a dx dq, which is defined in terms of this equation up above. So dx dq, and this x over q, that's a very complicated expression. So what we're getting here is, here's one power series which is unknown, but not that complicated looking, and I identify it with this other crazy power series. But the good thing is computers are very good at dealing with huge power series. They're happy to do combinatorics until the cows come home, or the cats come home, you know, depends how you're feeling. So we can take this complicated expression and do a bit of algebra, and it would be algebra that's sort of unpleasant to do on your own, but you can trust someone else to do it or have a computer do it. And it will just spit out for you the number of curves of a given degree in this quintic. So, you know, already kind of an interesting thing, things of degree 1, those are lines. So there are 2,875 lines in this quintic. And these lines had been found way earlier. That was already a known result. And by harder work, as you'll see written here, the degree 2, degree 3, and degree 4 ones had been found by very hard work. By degree 4, you're up into, oh geez, how many digits is that? A lot of digits. So you're getting to something that's really pretty unimaginable trying to do by hand. And this power series just spits out the answer for you, right? So this guy, what is that? Whew, that's a big number. I don't think it will help anything for me to try to say it out loud. All right. And as I'd said before, up to, I think now we've gotten up to d equals 11, we've actually found the number of curves of those degrees, and they do agree with the prediction from mirror symmetry. And I believe we know that if the numbers are finite going further up, they have to agree with this prediction from mirror symmetry, but we don't know if they actually are finite, so we don't know whether everything matches up. All right, so this is one example of how things work out. We're out of time, so just as well. Next time we'll try to talk, obviously, a very small amount of detail, just kind of an overview about maybe a slightly deeper explanation of what's going on here in terms of homological mirror symmetry and the SYZ perspective on mirror symmetry. All right, are there any questions? All right.